So this is chapter 2. This is our measurement unit. It is not a very long unit, but it is one of our more important units in that this is how we're going to do math in chemistry, okay? Because we're going to report things a little bit differently, and we're going to, be doing some different kind of calculations. So this is like kind of showing you how that's going to be used. So it is important. First of all, we're going to be using the metric system in here, okay? We will not be using the English system. That's just a cute little cartoon that I've been using for a long time. So first of all, in this class, there's no cussing. You may not use any of these 4-letter words. Okay? Inch, mile, yard, feet, acre, whatever. And never, ever, ever, ever use the F word. Not allowed. Fahrenheit. Okay? Keep it clean. We're going to be using the metric system. We will be using either Celsius or Kelvin. Okay? We'll be either using Celsius or Kelvin. Okay? So we do not use the F word in here. Okay? Also, there is no nudity in chemistry. So all of your numbers need to have units, no naked numbers. Okay? If you tell me the answer is 25, I don't know if you mean it's 25 grams, 25 degrees, 25 centimeters. You have to put a unit on there. Without a unit, the number is meaningless. Okay? Also, none of you are Harry Potter, so there's no magic numbers, meaning show me your work. And I want to be very, very clear on this. Okay? And I'm going to have it recorded, so someday I can say, look, go watch that, and it's recorded. If you do not show work, you will not get credit. Even if you have the right answer, I will give you no credit for it. Okay? And every year someone challenges me on that, and they turn in a paper that just has the answer, and you know how I give it back to them? A big 0 on it. Okay? You must show your work. I know that you can do some of this in your head, especially when we start doing this right now, and like tomorrow or the next day when we start doing some of the simple conversions. I know that you could do that in your head. However, I am training you for what is coming. Okay? I know what's coming down the pipeline. You don't. So trust me when I say, as simple as the setup is, do it to help you practice. Okay? As much as it may not seem like it sometimes, there is a method to my madness. Okay? So that brings us to the scientific method, which you have done since what, 2nd grade maybe? So we're going to gloss over it pretty quickly. That is why you have the crossword puzzle, because it's my way of saying, do you remember the scientific method? Most of you do, so we're good to go on. But these first 2 blanks, this scientific method is the way that researchers carry out their investigations. And it is a logical approach to problem solving. Okay? And of course, here's our flow chart. Ask a question, do research, hypothesis, that sort of thing. Okay? The steps to the scientific method. Okay, first thing is you're going to ask a question. After you ask a question, you're not just going to jump right in and do your hypothesis. You're going to observe or collect data. Most of the time it started out with, I noticed that when X happens, then Y happens, and that makes you question it. So you're going to observe and collect data. You next will formulate a hypothesis. Now, I prefer testable statement over educated guess. Your paper today says educated guess. I actually dislike that. Okay. The hypothesis serves as the basis for making your predictions and carrying out your further experiments. Once you have your hypothesis, then you will test your hypothesis, okay, in the form of doing your experimentation or data collecting, depending on what kind of hypothesis you have. Okay? Once you have tested your hypothesis and it proves to be true, then you go on to the next phase. However, if you test your hypothesis and it does not prove to be true, what do you have to do? Rehypothesis or change your hypothesis and test again. Okay? And then you test as many times as you have to reformulate your hypothesis, you do so. You never change your data to match your hypothesis. You change your hypothesis and retest again. Okay? Once you have gotten to that point where you've tested it over and over and over, there's usually 1 of 2 ways it could go. It could become a... That's new. I don't know what I did. Let's see if I can do it again. Nope, that was a fluke. Scientific law, okay, is a general statement based on the observed behavior of matter to which no known exceptions, okay, that's the clue there. A law has no known exceptions. In chemistry, large basis of chemistry is the law of conservation of mass. It states that mass cannot be created or destroyed in an ordinary chemical reaction. That has been tested over and over and over. We will test it most likely in a lab and find it that there are no known exceptions in an ordinary chemical reaction. Okay, when we get to nuclear, that doesn't apply as much. Okay, because that's a different kind of reactions because it's using the nucleus. Okay, a theory is a broad generalization that explains a body of facts. Okay, the reason it's still a theory is something about it has not been able to be proven, or there might be something that's not quite adding up, and so that's why it remains a theory. There are some theories that, quite frankly, might not ever become laws because there is no way to prove what that theory is about. Does anybody have an example of what they think that could be? The Big Bang Theory. They think they know, they have things to add, evidence of maybe what had happened, but there's no way we can go back in time and witness exactly what happened. Okay? Now, some scientists and some people in the media like to present theory as if they are a fact or a law. Okay? There may be a lot of the components that are, but then there's also that scientific question of maybe it is, maybe it isn't. So just keep that in mind when people are talking about theory. Okay? So when we are collecting our data, there are two types of data that you can collect. Both are very valuable and both are very useful. They're just different. Okay? First type is numerical in value, and we call that quantitative data. And quantitative data means something was measured. Okay? It always, remember I said no naked numbers, always has a number and a unit. Okay? So again, if I go into the lab and I measure temperature, I don't just write down 25, I would write down 25 degrees Celsius or 25 Kelvin. Okay? A qualitative means it is something that is descriptive or observed. And it's going to be something that's observed with one of your five senses. I saw the color change. Okay? I saw bubbles. I felt that it, got warmer. Okay? Those kind of things. So, for instance, if I went into the lab and I did a reaction and I felt the side of the container and it felt warmer, I would say it felt warmer. So that would indicate to me I had what kind of reaction? A chemical reaction, but I'm exothermic, endothermic. Sorry, I didn't specify. So if it got hotter, I would say it was an exothermic reaction. Okay, and I would do that based on my observation. However, if I measured it and said the reaction increased by 5 degrees Celsius, that would be a quantitative proof that it had been an exothermic reaction. Both prove it. I mean, obviously I can feel that it got warmer than room temperature, and so both would be a way to prove it. One's just qualitative, one's just quantitative. Okay? And to me these are fairly easy. Kids still kind of get them mixed up on a test, but this has that quantity kind of in it. Okay? So use your root word there. And this has like a quality. And an observation is going to be a quality. Don't do that. You don't need to do that. Okay? Precision and accuracy. On the surface, they seem really easy. But on a test, kids get them backwards all the time. Okay? For some reason, I don't know why. So, precision is the first one. And precision is the closeness of a set of measurements. In other words, can I repeat the same measurement multiple times? Okay? It's how well they agree with one another. Okay? Accuracy is basically, is it right? Okay? How closely does it agree with the correct value? Okay? Now, for precision, can you measure precision if you just have one measurement? No, because it's a set of measurements. But for accuracy, can I measure accuracy with just one? Yes, you can. So that's one big difference between them. Okay? So the best example is throwing darts. Don't have to do that left side. So here's my first dartboard. 1, 2, 3. The person throwing this, are they accurate? No, but are they precise?
Yes.
Yes. So they would have poor accuracy but good precision. Okay? 1, 2, 3. How about this person? They pretty much stink at darts, which is how I throw darts. Okay? They would have poor accuracy and poor precision. And then the last person, they win the tournament. Okay? They are both precise and accurate. Okay? They got it all going on right there. Okay? Random errors reduce your precision. Okay? Systematic errors reduce your accuracy. Random errors tend to be human errors. You messed up. And systematic errors tend to be the instrumentation. Okay? Now, just because an instrument is not necessarily very accurate, if you know that it's precise, you can actually still use that sometimes because that is built into the error or the machine. So let's say I have a balance and I put my little weight on there and I find out I have this little 200 gram weight that's exactly 200 grams. Put it on the balance and my balance reads 199. Okay? So it's not accurate. I'm off by a gram. Okay? But if it's always off by a gram, will that make a difference if I'm doing something where I measure the before and after value?
Yes.
No, because that 1 gram is built into both measurements. So when I subtract them, it's not going to affect it. Okay? So you can still use that instrumentation sometimes. Okay? And then reproducibility is precision. You check by repeating the measurement over and over. Poor precision usually results from poor technique. Okay? And then correctness is checked by using a different method. And then poor accuracy results either from procedural, maybe the procedure was just wrong to begin with, or something's wrong with the equipment. Okay? So that is precision and accuracy. Don't do that. Percent error. Put a star by this formula. You will use this formula off and on all year long. All year long. Okay? So if you're keeping up with your notebook, it's handy because it's on the first page of your notes. I'm recording. Okay. So this value right here, accepted value, is the correct value. What is published? Okay, what is published? The accepted value is what's published, what I would give you. The experimental value is what you would get. So this would be your value when you did the lab. Okay? What do these little bars right here mean? Absolute value. And in a nutshell, what does absolute value mean? It will never be negative, right? Okay? Because of that, some text will show accepted value minus experimental. Some will flip it and say experimental minus accepted. Because you're taking absolute value, it actually doesn't matter. Okay? Either way, because it's going to be a positive number when you take the absolute value. However, it's always accepted value on the bottom. Here's an easy way to remember that. Your value is suspect because you got it in the lab, so you're only going to use it once. The accepted or the real value is the true thing. It's more important, so you're going to use it twice, top and bottom. That's a way to help you remember that. So very quickly, we're going to do a little example. You can do it in your little margin. I'm making up these numbers. I do not know what the value of the density of copper is off the top of my head. Okay. So let's say we're going to do a density lab on Monday. And let's say your value, the experimental value for copper, you got 6.58 grams per centimeter cubed. And I tell you that the accepted value is actually 6.3 grams per centimeter cubed. So I want you to calculate what your percent error would be. So everybody do that real quickly, and then I will see if you're right. First person to get it, raise your hand. Anybody want to give me what they got? Yes.
4.4.
Yep, like 4.444%. So that is the correct percent error. Okay? So your scientific method is, if you can get it by the end of the period, great. If not, you can bring it to me tomorrow.